Okay, so let's get started. Um, as usual, feel free to stop me at any time and ask me, any questions. So the topic for today is intrusion detection. So we have talked about, uh, software vulnerabilities and attack strategies and whatnot. So a lot of what we discussed in the course so far relates to finding vulnerabilities and fixing vulnerabilities and so on, and then exploiting vulnerabilities. uh, so if you're in the position of trying to uh, prevent attacks, then your first option is, of course, to try to find and patch the vulnerabilities before they're exploited. But many times, you cannot stop all attacks, and then intrusion detection is sort of the method of last resort that is used to at least detect attacks that get through all other defense mechanisms you have put in place. So just a little bit of a background when we talk about attacks. Attacks are generally divided into three main categories. So there is probing, which is sort of the first step, right? So an attacker wants to probe the target system to identify the vulnerabilities, and probing often uses port sweeps, which is a process of trying to, uh, connect to various ports to see what services are running. Sometimes, it's not a actual connection, but just a single packet that's sent for probing purposes. And once the attacker finds out what services are running, then they go on to gather more information about the applications that are running. So this is uh, application fingerprinting. So they can try to find out a particular version of the software that you're running, because vulnerabilities are specific to specific versions of applications and operating systems, and therefore, if the attacker is going to carry out an attack, they need to first um, get an idea of what version of application that they're running. So a general class of attack is denial of service, right? So uh, denial of service doesn't really help the attacker directly. What it does is it makes the target service unavailable, which means that if the victim business is taken out, or it's not able to serve its customers. And so that's the goal. So this denial of service is often used in conjunction with uh, you know um, ransoms. So you can mount a denial of service attack on a service, on a company, and then ask them to pay up, or else you will bring their site down. So denial of service is becoming increasingly hard these days, because more and more uh, companies outsource their websites to various providers, and these providers give the companies points of presence all around the world. And in addition, these services are able to basically um, uh, deal with, or block these denial of service attacks. So by and large, these days, ransom requests are associated with, again, the word ransomware these days, you immediately recognize it as some way to, encrypt or remove files, and then ask for ransom to be paid in order for those files to be restored. So a simple denial of service attack, where you're trying to saturate the network of some victim service, that is not a very common occurrence these days. And finally, the attacks that actually give significant access to the attacker, they all fall in the privilege escalation category, right? So there are two categories of privilege escalation. One is called remote to user, meaning that the attacker starts out having no access to the victim machine, and then they are able to typically make use of some system vulnerability to gain access to that system as a local user, right? And user here means non-administrative user, right? So it does not have admin privilege. The second type of privilege escalation is user to root. So a normal user is now able to get administrative privileges. And very often, the term privilege escalation is more commonly used with this user to root escalation rather than remote to user escalation, because sometimes remote to user is sometimes called as has multiple terms. One term that's often used is getting a foothold. The attacker starting with no access to the system somehow is able to run some code on the target system, and that's called getting a foothold. Typically, an attacker would combine these two steps so that they ultimately have the administrative privilege on a target machine. But sometimes they don't need the administrative privilege in order to carry out their attack, and they may just stop with a remote to user attack. Okay, so so that's about the different classes of attacks. And intrusion detection systems are designed to identify all of these categories of attacks. But we will focus primarily over here, right? These privilege escalation attacks, which typically involve exploiting vulnerabilities in some applications. So that brings us to the discussion of intrusion detection. So the idea here is that no matter how careful you are, how well you configure the system, and how careful you are in terms of patching your system and fixing the vulnerabilities and so on, in spite of your best efforts, some attacks might still get through, and you need to have a mechanism for dealing with those attacks. Okay, and the intrusion detection is this, is aimed at detecting these attacks that get through all other, defense techniques. And therefore, it is a solution of last resort, right? So you prefer that the attack be stopped by one of the other mechanisms you implemented. So this is sort of the catch-all, the last step, last effort for you to try to catch an attack. And the basic idea here is that, or rather the assumption behind intrusion detection is that attacks are somehow different from normal use of the system. And so the goal is to identify these differences between normal use and an attack. And that's what you're trying to detect when you say you want to do intrusion detection. So a couple of terms. Detection rate means what fraction of the actual attacks are detected. And then false alarm rate, which relates to how often you claim there is an attack when there isn't really an attack. And there are multiple ways to measure false alarm rate. Some vendors try to say, you get so many false alarms in a day under certain conditions. Others might say a certain, what fraction of the normal behavior is flagged as attack. So people might say, well, you have a false alarm rate of 0.01%, which might mean that only 0.01% of normal activity will be flagged as an attack. But a catch here is that what is, considered as a behavior. So for instance, if you have a intrusion detection system that's looking at system calls, and you say 0.01% of the system calls, raise an alarm, that's a disaster, because that probably means you're going to get, hundreds to thousands of system call alarms every second, right? And you can imagine that that's a total disaster. So when you measure it as a fraction of normal behavior, it really matters what your denominator is. Another way to measure, which is sometimes called as false alarm ratio, is you ask the question, okay, suppose I get something is reported as an alarm. What is the probability that it is not an attack? Okay, and most of the time, there are lots of false alarms. So 9 out of 10 times, you expect that the alarm is actually a false alarm, and most of the time it's not really an attack. So the false alarm ratio tends to be quite high. The problem with that is that if you are an operator looking at these alarms, you get used to the fact that most of the alerts are false alarms, and so you tend to not to pay much attention to them, and so therefore it's easy to miss out real attacks. So this false alarm rate is sort of the biggest problem for intrusion detection systems, because existing solutions generally have high false alarm rates that make these intrusion detection systems very noisy and not that helpful to users in practice.
Excuse me?
Yeah.
How do you even calculate detection rate? It seems kind of like a catch-22, where if you're not detecting that you're being attacked, then how can you then measure if an attack has occurred?
Right. So you would one way to do that is to measure against a specific data set, or known under certain known conditions. Right? It can be measured given a data set. Nobody can tell you in advance that we will detect 95% of all attacks, right? And that's what you're pointing out, and that's correct. But it can be measured after the fact.
Okay, thank you.
So in terms of the methods used for intrusion detection, there are, historically, there are 3 broad categories, right? So the oldest technique is what is called misuse detection. And the idea is that you will, because you have seen attacks in the past, you can, very precisely identify how these attacks were carried out. And that is why this is called misuse, because, well, you're trying to capture the behavior of specific attacks. And as soon as I describe it this way, it's easy to see what the problem could be. And that is, if there is a new attack that you haven't seen before, then, well, there is, because you haven't seen it before, there is no, pattern that captures this attack. And therefore, the new attacks are not detected, right? So misuse detection is primarily aimed at detecting attacks that you have seen in the past, okay? So in addition to not being able to identify novel attacks, there is also the problem that attackers can very easily change the details of the attack that they carry out, right? So if they know that you're, looking for a specific pattern, they can change the attack in minor ways. Maybe they reorder the steps, or they add steps that are not really important and are not relevant to the attack, but confuse the detection system anyway. So as a result, misuse detection is something that has a lot of gaps and can easily miss real attacks. But on the positive side, when you do see a match, you can be reasonably certain that you have an attack. And in addition, because you have exactly described some attack in the past, you know exactly what the attacker was trying to get at. So you have a much better understanding of what the attacker is trying to accomplish if you are using this kind of misuse detection. So the other approach called anomaly detection starts off at the other end of the spectrum, right? So you don't know anything about attacks. Instead, you are using some machine learning techniques to learn a profile of normal behavior. Okay, so what is benign or normal behavior of the system? And then once you have learned that normal behavior, then you can try to detect attacks as deviations from this normal behavior. So the advantages and disadvantages of anomaly detection are complementary with misuse detection, right? So because you are going to flag anything unusual as attack, you have that makes it possible for you to detect, unknown attacks that you've never seen before, right? At the same time, you may have a high false alarm rate because, any behavior that you haven't trained on can potentially can be flagged as an attack. And very often, there are certain types of system behavior that are rare. So for instance, something goes wrong with your server. Something is wrong with your server's disk or the network or, something else. So these sorts of behaviors are unusual and they will be reported as an attack when in fact, it may be perfectly reasonable. Or you may have a situation where, there is a deadline and a lot of people are accessing your server and well, that looks abnormal and you may report that as an attack. So again, the problem with anomaly detection is generally that it has a high false alarm rate. And by the way, the reason why anomaly detection works is because of the fundamental assumption in anomaly detection, right? Which is this, right? Whenever there is an attack, the behavior of the system changes in some way, right? So again, you're not saying that the system the behavior is going to change in every way, but there will be at least some changes. And so if you are monitoring a wide range of features associated with the system, then you should be able to detect attacks, right? So as a practical matter, detecting attacks is quite easy with anomaly detection. The problem is that the false alarm rate is so high that even though something is identified as part of an attack, you would typically, the person who is looking at these alarms would generally not be able to make out the distinction between a real attack and a false alarm, right? So you know that there is an attack taking place, but you don't really know, where it is or what exactly it is doing to your system. And so it's one of those things where you have some idea that there could be something going on your system, but not enough visibility to be able to narrow down where the attack is or be able to do something specific about it. So there's a third class of techniques, which is either called specification-based or policy-based detection. And the idea here is that you have some specification of what is allowed behavior, right? So as an example, think of access control policies on your system, right? So on your, let's say, files. So the access control policies specifically say, how you expect those files to be used. Now, if you can generalize that and then think of what is, legitimate use for, various applications, then you may be able to quantify what is, not a legitimate use, and that could be triggered, that could trigger alarms. And so in some ways, misuse detection and policy detection are similar in the sense that you need to have an idea of what it is that you're looking for, right? The difference is that you can think of a misuse detection as some kind of a blacklist of disallowed behavior, whereas policy-based detection, you can think of it more like a whitelist of allowed behaviors, right? So that's the kind of distinction. And so it is possible to develop these policies that can broadly identify some of the disallowed behaviors, okay, without having to be very specific to attacks. But in the real world, by and large, when people talk about intrusion detection, they're talking mostly about anomaly detection and misuse detection. Any questions so far? Okay, so moving on. So intrusion detection, there are two main techniques or algorithms that are employed in intrusion detection. Pattern matching is a technique that is typically used with either misuse detection or policy-based detection. And machine learning is the technique that is used for anomaly detection. Okay, so and machine learning, well, there are various categories of machine learning algorithms that aren't necessarily specific to intrusion detection. Although there is one thing that that is important in the context of intrusion detection, which is that we have to be aware of the fact that the attacker is actively trying to evade your detection techniques, right? So whereas typically in machine learning, you are not really worried, you are not focused on these kind of adversarial behaviors, right? So you don't think of the typical case for which machine learning algorithms are developed and tuned for is benign use cases. Adversarial use cases where some attacker is specifically trying to fool the learning system, that is unusual in many settings, but it is really the setting for intrusion detection, because we are really trying to detect attacks. Attacks are by adversaries, and adversaries are always trying to evade and obfuscate and hide their activity. And therefore, whenever we use machine learning techniques, we need to be using techniques that are robust against adversaries, right? So adversarial machine learning is a whole new area that's under active research these days, and it's basically that kind of machine learning that should be used in the context of intrusion detection. And if you look at past research in intrusion detection, you would see that by and large, a lot of techniques in intrusion detection have used relatively simple machine learning techniques. And the reason for this is because then you can reason about whether these techniques are robust against adversaries or not, right? So if you cannot reason about adversarial robustness, then just don't use it in this context, because the attackers are just very easily going to evade your technique. So the second thing when you talk about intrusion detection is Well, you're going to use learning or policies or patterns, but what exactly are we writing these, what do these policies or patterns or behaviors deal with? And in the very early days, by which I would say 30 years ago, the focus was almost entirely on user behaviors, because in those days, systems were generally mainframe type systems, uh, you know, um, large servers that are used by multiple users, and there isn't a whole lot of networking that's going on, and therefore the attacker is usually one of the users that already has access on the system, and therefore the focus was on identifying users that are behaving in unusual ways. Unfortunately, this task of finding insider attacks or finding abnormal user behaviors is quite hard, because user behaviors tend to be much more variable than behaviors of system components. In particular, if you think about an application has much more narrowly defined behavior as compared to users. And so in the early days, intrusion detection really didn't take off because the techniques had such high false positives that nobody could really use them in practice. But with the advent of smaller computers and single user machines and applications and network servers and so on, the nature of the attack changed, and very often the attacks were involved vulnerability exploitations on applications. And so now if you're exploiting the vulnerability in an application, an attacker is doing this in order to use that application to do something that the application wouldn't normally do. So for instance, maybe the user is trying to run a shell on a victim machine, but they are doing this by exploiting, let's say, a web server, right? So a web server normally would not run a shell. And so if you are monitoring the behavior of this web server, any attempt to run a shell, interactive shell, will stand out. And therefore, it is possible to identify these types of vulnerability exploits with a fair degree of confidence. And so this, by focusing on the behavior of systems, intrusion detection techniques were able to become much more practical. And so the whole research in the area became much more popular at that point, because again it becomes possible to produce results that are useful to system staff and system security administrators and so on. So again, so you say system behavior, but what are the things that you're observing? And so far, I gave the example of applications and observing applications behavior. But we can take a broader look at it in a broader sense and divide it into two categories. One is observing events at the network layer and observing events that are taking place on a single host. Observing at the network layer is very convenient because you can just plug in a device, an intrusion detection device on your network, and it can monitor all the activities on the network and trigger alarms and whatnot. So the deployment becomes really easy and unintrusive. But unfortunately, over time, there has been more and more use of encryption, and various other factors have made network-based intrusion detection less and less useful these days. So in recent times, there is much more reliance on host-based techniques, which are observing the operation of applications and the operating system on a end host, and that is how intrusions are detected. Okay, so there are many ways to detect this, and the two ways that are most popular are one, intercepting system calls at some level, either in the application or at the operating system, or using a system auditing facility which would record all the important events that are going on. Okay, so typically auditing services would record information that is similar to system calls, right? Because most security important events are like system calls, such as starting a new process, reading a file, connecting to the network, sending some data over the network. All of these require system calls. So most system calls have a security implication. And so when you talk about auditing systems, you end up still recording things like system calls. So on Linux, there is a service called AuditD, okay, which you can install and enable, and AuditD will record a lot of information that you can examine later on to detect attacks. So because as I said, network intrusion detection is not that effective anymore. So I won't spend too much time discussing network intrusion detection, but instead I'm going to focus on host-based intrusion detection. And again, as I said, system call-based techniques are most common because most of the activity that you're interested are related to, are going to manifest themselves as system calls. So when I say system call based, it doesn't mean that every system call needs to be, examined. So host-based IDS are configured to make use of some subset of system calls. So for instance, typically you're interested in things like exec and fork and so on. And second to that, you're interested in system calls like open and connect and accept and so on. And then thirdly, you may be interested in things like read and write. Okay, you can imagine that reading and writing is probably not that important. It's much more important to know about opens, and even more important to know about process startup and termination and execution of new applications and so on. So again, in the interest of time, what I'm going to do is I'm going to talk about a particular technique for anomaly detection that is using system call data. Okay, because again, looking at system calls is a very good way of understanding application behavior, and looking for anomalies in the system call sequences is a well-established way for detecting attacks. So I'm going to talk about a particular technique for learning program behavior in terms of the system calls they make, and how that can allow you to detect attacks. Okay, so So again, it's well known by now that looking at system calls and sequences of system calls provides a good way to characterize application behaviors, okay? Application behaviors as they relate to security, okay? Now, the question is, if you want to learn, what is a good way to represent this information, right? So in machine learning terminology, this is called a model, right? So what kind of a model are you trying to construct, and what is the algorithm that you use for constructing this model, okay? So people have looked at this problem for quite some time. And in the literature, the simplest technique for learning properties of sequences is called the n-gram technique. So the n-gram, basically what it says is that if you have a sequence, I guess we'll see an example later. So n-gram basically looks at substrings in the sequence, right? So if you write out all of the system calls that an application makes, then you can take substrings out of this sequence. So substrings of length n, and that is called an n-gram. And you can say that the behavior of a program is simply the set of all n-grams that it ever makes during normal activity, okay? So then there are other types of models that have been discussed in statistics, like Markov models, and then there are techniques called data mining and so on. I won't talk about them in detail, but researchers have looked at many of these types of techniques, and they find that the simple n-gram technique works quite well, okay? So here is an example, right? So think of, here is a simple program for, just a toy program. And here, all these S1, S2, S3, S4, S5, these denote system calls, okay? So now if you look at a sample execution of the program, it may execute S0, then S1, then S2, okay? Then notice that this is an if then else statement. Therefore, if you execute S2, then you won't execute S3. So after S2, you end up going to S4, and then you may go to S5, okay? And after S5, then you may go back to the beginning of the loop, and once again, you may execute S1, S3, and so on, all the way until you, exit from the bottom of this code sample after executing S4, okay? A different execution sequence may never execute this loop at all, and so it may go through S0 and just jump past the end of the loop, and so you will get S0, S3, S4. Now, looking at these two sequences, you can write out what are the 3 grams. So S0, S1, S2, that is 1 3 gram. Then S1, S2, S4, that's a second 3 gram. S2, S4, S5, that's a third 3 gram, and so on. And so you can, tabulate all of these 3 grams and then say, under normal conditions, I should see one of these 3 grams, right? So this is how you learn normal behavior of the program. So, so that's one technique. Now, here are some of the problems with using this kind of n-gram method, because one of the problems is that the number of possible n-grams is exponential in n, right? Because if you have a sequence of n characters, right? So the first, if you have k system calls, then the first element in this n-gram can be one of k system calls. The second one can be one of k system calls, and so on. So you will have k to the power n possible n-grams, right? So which means that if n becomes, even slightly large, the number of distinct n-grams is going to be very large. So one of the questions is, can we do better, right? So one of the things we did a while ago is to suggest that if you're trying to model behaviors of programs, things like finite state automata are a much better way to model program behaviors, because if you go back and look at the simple program, right? So if I were to write down what this program looks like, it has things like loops, right? So this picture kind of shows you some, the structure of this program. Maybe there are, further, if then else conditions inside the loop and so on. But this picture of the program, or what is sometimes called the control flow graph of the program, looks very much like a finite state machine with states and transitions and so on. So one of the questions is, can we get a more accurate model that uses that constructs a finite state machine rather than something like n-grams. And turns out that there is actually a very simple way to do this, right? So historically, the problem of learning strings, finite state machines from strings, is known to be a very hard problem, right? So it's an NP hard problem. But the reason why it's hard is because people were looking at the problem as learning just the with just the string information. But in reality, what happens is that when you look at programs, you actually have additional information. So for instance, if you look at this program, there is system call S0 is made from line 1, right? And system call S1 is being made from line 3. Or if you look at the binary of the program, then S0 will be made from a certain location in the program. S1 is being made from a certain other location in the program, and so on. So when we look at the program behavior, in addition to looking at the system call itself, we can also get the location from which the system call is being made. And once we get this information, we can use that to construct something like a finite state machine here. So for instance, this one, you see from line 1, or rather this one says that from, let's say this is line 0. So this part of the finite state machine says that the program goes from line 0 to line 1 after making system call S0. It goes from line 1 to line 3, right? So from here to here. That happens after making system call S1, and so on. So by utilizing the information about where the system calls are being made from, it is possible to construct a finite state machine like this. And the advantage here is that you can very quickly capture the entire behavior of the program without having to run into this exponential problem that you have with n-grams, right? In particular, if there are n locations in the program, there are going to be only n states in the finite state machine, right? So the model that you are learning is going to be linear in the size of the program, and that makes it much more compact, and also makes it faster to learn. At the same time, the model is richer and captures, long-term behavior. So, for instance, that after making S0, after a certain number of system calls, you can make S5. On the other hand, if you just look at the n-grams, n-grams don't say anything about, whenever you see S0, you won't see, okay, let's see S2, right? Or S1, right? So from S1, right, there is this kind of transition that can take place. You go do S1, then S3, S4, S5, and S4. This long range behavior, which consists of 5 system calls, is not going to be directly captured, because here everything that you capture here is about, is a property of a string of length 3. Whereas if you look at a state machine like this, then you are not limited in terms of how far the these states are. They can be arbitrarily far, and you'll still know that this particular system call can be executed after this particular system call, right? So there are so the model is richer, and at the same time it's smaller and more accurate, and so on. Okay, so any questions? So I wanted to give you some idea of how intrusion detection techniques work. Obviously, we are not going into this topic at the same level of depth as some of the other topics that we have covered so far. We are obviously reaching the end of the course. We have just one more lecture left, so I'm trying to quickly introduce a few more topics before we finish off the lectures. So any questions about this topic or some of the earlier topics? Okay.